Okay, you got it.
Okay, good evening one and all. Jim Simpson, Climate Realist, the 5 Doc. Thanks for joining us again this evening to listen to Ivan Kennedy with an hypothesis regarding climate change and the impacts of irrigation globally on global warming. Thank you.
Thanks very much, Jim. And I'd also like to thank the audience, because to a certain extent this is going to be some repetition. But since I last saw you, I've presented at the University of New South Wales at the International Conference, and I even met Gavin Smith from the Space Centre, NASA, the Goddard Space Centre, and he did say to me that at least my hypothesis was new. So that's hardly words of praise, but at least it did grab his attention for a second or two. What I want to do tonight is, in about half an hour, is run through that talk again, but also add to it what I've learned as a result of going to the conference, and in thinking and in actual research since that time, testing the idea that irrigation is a significant part of global warming, and that perhaps that's something that we need to think about. In the talk, I pointed to the outgoing long-wave radiation from the NOAA satellite data, showing that certain countries are heat vents for the Earth. And in particular, the ocean zones, here also shown in red, are where air is descending, which has been dehydrated, coming from the tropical regions. So when we look at this, we see that all of the countries that have water deficit vent heat to space. This is the heat actually leaving the Earth, which has to balance up the heat coming from the sun warming the Earth. And the two ultimately should equal one another. Whereas countries like China, which are very moist and have a moist, humid atmosphere, release relatively little heat to space. And this is consistent with the idea of the radiation coming from the Earth's surface, shown here in blue, and the radiation actually going to space, shown in red, much of which has been absorbed by water right across the spectrum, but also by carbon dioxide, ozone, and other greenhouse gases. So remember, the red one is the radiation that actually ends up in space. So the fact that the carbon dioxide line here is lower indicates that the radiation from CO2 is from the top of the atmosphere, where the atmosphere is very cold. Radiation from water goes to space at lower altitudes. So this is the greenhouse effect. The amount of radiation that's absorbed and transferred to the molecules of the atmosphere is the greenhouse effect. This is radiation, if those gases were not present, would go straight to space without being absorbed. And this feasibility analysis predicting global radiative forcing by 20th century irrigation water uses the Stefan-Boltzmann equation and calculates from the regional outgoing long-wave radiation with a 288 degree Kelvin surface of about 300 watts per square metre. And then by looking at emission at the surface or at 6 kilometres where it's colder, you can calculate a factor that will enable you to see how much less heat is being emitted to space as a result of that greenhouse effect. And if you consider that water is responsible for over half the absorption of heat from the Earth's surface in the atmosphere, and then take into account the fraction of the Earth which is irrigated, you can actually calculate a global radiative forcing, which now give as 1.02 watts per square metre. That's for the whole Earth. So that's the hypothesis, and it tends to be supported by that analysis. If we look at water consumption from 1900 to 2025, the projection, not 2025 yet, there's been about a tenfold increase in water use by the human population, and really that's roughly in proportion to the increasing human population on Earth. And looking at irrigation itself, in 2009 it was projected by the FAO that there was something over 3.1 million square kilometres of irrigated land on Earth. Now that's not very much of the total land, it's about 2%, but that's not the point. We're not talking about a huge amount of extra heat being trapped. The annual increase in carbon dioxide has been increasing. This is as measured in the atmosphere, about a similar percentage, a little bit less, about 1% a year, whereas irrigation has been going up of the order of 2%. And typical irrigation, particularly in the drier areas, looks like this. Often groundwater. More and more groundwater is being used. This is new water that has never been in the ocean or never been in the atmosphere. And the other 2/3 of irrigation is water from dams, from riverine systems that otherwise would have flowed to the ocean, but is now prevented from doing so, and it evaporates on dry land. So this is the nub of my hypothesis, that this extra water in the atmosphere, in dry atmospheres, adds extra greenhouse effect to the Earth in terms of trapping heat. And water, particularly near the surface, is very, very efficient at trapping that heat and maintaining a warm atmosphere. I'm not saying it's heating the surface, it's just maintaining a warm atmosphere. If you go out to the centre of Australia in winter in a very dry atmosphere, at night the heat drains out of the atmosphere because there's no water in that atmosphere. And you freeze unless you've taken proper care with your camping situation. We've frozen out there on many of our trips to Western Australia, going back to see family. So summing up, irrigated dry areas significantly raise local humidity for months during the whole crop growth. The evaporation of the crops is putting water into the atmosphere. It's not just evaporation from dam surfaces, but it's the whole biological system. And once that heat is absorbed in water vapour plumes, it heats up the nitrogen and oxygen of the atmosphere. These are the gases that contain most of the heat of the atmosphere, far more than water or even carbon dioxide. Carbon dioxide is minuscule by comparison. So because of irrigation being in dry areas, you get the maximum greenhouse effect. The lower the water content of the atmosphere, if you add an increment of water to it, at low humidity, you get the maximum greenhouse effect. So as long as extra water is being added to the atmosphere, extra heat can be retained. The magnitude of this effect increases linearly with the increasing area. So unlike the heating effect of carbon dioxide, which is supposed to increase logarithmically with concentration, with water it will go up linearly. So according to the area. And here, this gives a table of the annual fresh water vapour from irrigation, and so on. I don't think we need dwell on it, but the critical thing here, though, is that there's 90 cubic kilometres of extra vapour in the atmosphere at any one time from irrigation. That's taking into account the fact that water in the atmosphere only hangs around for about 10 or 12 days. Particularly in dry areas it's longer. Over the ocean it's only about 7 or 8 days before it rains out. But nevertheless it does stay there for a couple of weeks, particularly over dry land. So that means it's exerting greenhouse effect from that 3,000 cubic kilometres a year, but only 90 cubic kilometres is actually in the atmosphere at any one time. So let's not dwell on that. I made the analogy with the El Nino global warming and the La Nina global cooling. During the La Nina, water is evaporated from the warmer Pacific Ocean, elevates the atmosphere, reduces the outgoing long-wave radiation above it because energy has been trapped. So that means it's not a heat vent, it's less of a heat vent. And then, of course, that air then dehydrates in rain, is dried further at the high height, and then descends over countries like Australia. So we have our periodic drought periods, sometimes which are much longer if you heap up El Ninos on top of one another. But during the La Nina, this is all reversed, and we then get more rain over Australia. So the water that goes into the atmosphere during the El Nino comes out during the La Nina. So you get a significant increase in the amount of water in the atmosphere. And that's effectively my model, that irrigated land will have a greenhouse effect above it, reducing the outgoing long-wave radiation, whereas dry land will have low humidity and much more outgoing long-wave radiation and less greenhouse effect. The greenhouse effect is given by this G factor, and that's calculated by the heat emitted by the surface minus the heat going to space divided by the heat leaving radiatively from the surface. And if we compare different localities, Nanjing in China, which remember was in a moist area with very little OLR, with Quetta in Pakistan, Baluchistan it used to be called, and you can see that even though the surface temperatures are similar, the outgoing long-wave radiation above those sites are quite different, and the greenhouse effect above them is also different. The greenhouse effect is much greater over Nanjing than it is over Quetta. If you go to Singapore, similar surface temperature, a bit warmer, the outgoing long-wave radiation is even less, and the greenhouse effect is now something like half the heat that leaves the Earth's surface radiatively. So that's so the conclusions and takeaway messages. This is more or less the end of my talk. I made the point that this was an overlooked source of warming. Could be of the order of 70 watts per square metre. It's a linear trend globally, and it could eventually exceed the effect of increasing trend of carbon dioxide and climate change. In the audience was Andy Pittman, who's the CEO of the New Climate Centre, and at the end of my talk he made comment and he also challenged my point that this wasn't included in the GCMs, that irrigation wasn't included in the GCMs. He did admit that until recently that was correct. But it is now included in one of the Goddard Space Centre models, which I found after the conference. And I've taken that on board. But it's just a model, it's not experiments. So from that point of view, I'm not convinced. In fact, I think the model has flaws. And so I certainly don't see that as proof of this because I don't think the model is limited. It can't deal with everything. So if the magnitude is confirmed by field experiments, that's my point. Emphasis should be placed on achieving water use efficiency in the growing of crops to minimise this kind of warming, provided you think it's serious enough to deal with. We might be happy enough to have a bit of warming. We have to work out what the ecological and other effects are of that warming before taking precipitate action. But the point about water is it's manageable. We can manage it. We can do something about it. And we'll see an immediate effect, I would say. So this was the last slide in my talk. Just summing up, do experiments, predict and measure the area affected, humidity, OLR and so on, all of those factors that need to be taken into account. And then promote water use efficiency for greenhouse credits. Not just carbon dioxide, carbon credits, let's have greenhouse credits. And let's confirm that they actually scientifically do what they claim to do. There's no point in spending money doing things that are not going to work. Okay, so where do we stand? Since that time, and as a result of the conference, I met Keith Potts. He's a company director in Adelaide, but he worked with the oil or gas industry. And in 1974, he was in the centre of Australia, in the Simpson Desert, planning to drill for oil or gas. I've forgotten which. And on halfway through January, the heavens burst open. And Lake Eyre received 6 metres of water in about 2 weeks. This all came down from Queensland, from the Simpson Desert, from all that area. A huge amount of unusual water in that area. And of course, Lake Eyre, we do have these floods from time to time. Just going back though, before getting onto that, I should address this slide. This slide is already included in my talk, but this shows the correlation between the increase in temperature, temporal increases in temperature, and the outgoing long-wave radiation. This is for the whole Earth on a zonal basis. So here in red, where we have less heat going to space, the temperature increases. And there's practically a one-to-one relationship between this. Because if you look at the watts per square metre, they're going up about a total of 4 watts per square metre during an El Nino, La Nina cycle. So that means that amount of forcing is occurring during the El Nino because of the extra water in the atmosphere. And you can calculate this if you take, and this is something I've worked out since the conference. In a discussion, I talked to about 50 people at the conference, and I gave them a handout and invited them to come to my talk. And I think about 25 did. So, but since it was the last talk in the conference, I think that was a wise precaution on my part, because last talks in a conference very frequently have no one more than the convener or the chairperson, together with a couple of your friends. But I had Andy Pittman there, and he was very critical, and another one of his colleagues was also super critical on the basis that the amount of irrigation water is so small compared to the total cycling of water in the atmosphere. But I pointed out to him that that's totally irrelevant, because we're talking here about a small change in temperature. We're not talking about a large change in temperature. If you look at the Earth, the atmosphere contains 12,750 cubic kilometres of water on average. In an El Nino, that goes up about 250. In a La Nina, it falls 250. So it's oscillating between 12,500 and 13,000. That's about a 4% change in water content of the atmosphere. And if you calculate for the El Nino, that's 4 that amount of forcing, you get a 1 degree temperature change. That's the quantity of water, about 510, that's about 4% of that 12,000. And so I would expect it to change the temperature by the greenhouse effect of water, that is, by 4%. And that's precisely what it does. Every time there's an El Nino, you get an increase in global temperature because of the extra water in the atmosphere. Looking at the atmosphere as a whole, the greenhouse effect from water is regarded as 23.1 degrees, according to my calculation, which is pretty close to most other people. And that's caused by a forcing in watts per square metre of about 110 watts per... This is heat that is trapped on the Earth and doesn't go straight to space because there's water in the atmosphere. So this seems to be a linear relationship. This surprised me. I thought surely it won't be linear, but it is. As far as I can see, at least with the data I can command, and unlike the case for carbon dioxide where you can't find any such data to get direct linkages in warming and a greenhouse substance. And if you take irrigation into account, my estimate that there's 94 cubic kilometres of water in the atmosphere at any one time as a result of irrigation, that suggests that I should get about a 0.2 degree increase in temperature. Now that was pretty well my initial prediction. So this is something that I've learnt at the conference, and it's enabled me to, if you like, advance the hypothesis. Looking at irrigation in Australia, this is what's called the cotton map. Every year the cotton farmers indicate which of their fields are being irrigated, and this is done so that nearby farmers won't drift pesticides onto their cotton crops because cotton's very sensitive. So having such a map, and nearby farmers growing wheat or whatever, or sorghum, can be very careful with their pesticides. And often the cotton farmers and the sorghum farmers are the same anyway. But it's just a... so if you look at the situation near Narrabri, this is what the fields look like. I've spent literally months working on these fields doing environmental chemistry, and my students, about 10 of them, doing PhDs. So we know this area very well. But the point I want to make, though, is that the irrigated area is very spread out. So if you're working out how much area is actually affected by irrigation, it's obviously got to be more than the acreage or the kilometres squared that are irrigated. And I think that was one of the problems with the model that Andy Pittman more or less directed me to, and it's not taking into account the way that water in the atmosphere will drift and rotate and cover a much bigger area, so the greenhouse effect of that water can be amplified. The fact that it's diluted shouldn't matter, it'll just make it more effective, because the more diluted it is, the more effective it is, a greenhouse effect. If it's all concentrated above a field, the extra water doesn't make that much difference. So there we are. And Keith Potts, who had been in the flood of Lake Eyre, and they came back 6 months later to look at the site. They got a bulldozer out and had to put a strip on the top of the ridges. But when they looked down onto where they wanted to do their work, the windsock was just coming out of the water on the previous airport. So they had to give that idea away. And it was really 2 or 3 years before the area dried out sufficiently that they could get back in there with their bulldozers and drilling equipment and so on. This is obviously from one of those satellites we were talking about. And this is the Simpson Desert, and water sort of fanning out into the Lake Eyre area. So it's a real phenomenon. I did have some pictures that I took of clouds on the way there when my wife and I went to Lake Eyre in 2012, but I didn't have time to get them into the presentation in good quality. But that's another effect. This is something from the internet I just downloaded recently. Everything's dry at the moment. There has been some rains in Queensland and a bit of water moving in that direction, but it's not going to be a big flood. That's what it can look like. No wonder. Now, Keith Potts pointed out to me the existence of this tool. It's NCEP, NCAR, reanalysis data. Any of you can go to a website and do these plots, and it'll only take me 5 minutes to train you to do it. And I wasn't aware that you could do this, but it enables one to measure things like the OLR, the humidity, relative humidity, specific humidity, temperature, wind speed, all these sorts of climate meteorological phenomena from a data set that is now available to the public. And you can plot the result just by clicking on plot, and it appears about 5 seconds later. So I then just copy the results into, and what this shows is that if we subtracted the OLR from 1978, a dry year, from 1974 when the lake is flooded, as well as all the land around it to the north, we find this extra OLR occurring in the dry year. So that shows that in the wet year, 1974, there was much less OLR, that is, much more greenhouse effect. So I regard this as pretty good evidence. This is evidence, this is experiment. It's a natural experiment. It's not the ideal scientific experiment where you make a hypothesis and then do a new experiment. But when I did this experiment, I didn't know what the result would be. I had no idea what the data, so there's no way I could have biased that outcome. If we look at 1978 versus 1973, the year before the flood, we find that there's some bit of a signal there, but it's relatively minor. It's nothing like that was generated by this huge flood with all the extra water in that environment. What have I done here? I've even tested here 2 flood years. 1984 was also a flood year. And when I first saw this, I was a little bit disappointed. But when I looked at it a bit closer, the flood in 1984 was from the south. No water from Queensland, it was from local rainfall in South Australia. And it flooded Lake Torrens, and then it flooded South Lake Eyre, and then the water went into... But it was a lot less than in the 1974 flood, La Nina flood from the north. So that just shows that you can get discrimination on that. And also looking at this, we've got relative humidity at 300 millibars pressure elevation, effectively elevation. So all that sort of data is available. That's just telling us that that's just telling us that in the dry year, in the drier year, there was less humidity in the atmosphere. That's integrating it for the whole year. So there was only really water going into the atmosphere for 6 months in 1984. And that's very well covered in a paper published by CSIRO. So I intend to do more analysis on that. You can also get, this is again is plotting specific humidity at 300 millibars. It looks pretty similar to the relative humidity as you'd expect, but the specific humidity is the weight of water per kilogram of air, whereas the relative humidity is the percentage saturation, and they should correlate quite well with one another. And looking at, and you can plot the winds, the wind speeds. This is the difference between the 2 years, so that just shows that 1984 on average had stronger winds in this direction, but the winds are always in that direction in these 2 years. And this is 1978 minus 1974. That's again showing the 700 millibar relative humidity. So there's a huge amount of drier air in 1978 in the centre of Australia compared to the La Nina year when... Now, of course, all this is not really unexpected. I won't keep on doing that. But to me, that was a really good outcome from the conference. that we were able to get this result, which I think is publishable. I'm certainly going to try to publish that in a letter to one of the prestige journals, together with other material. So we've got direct quantifiable evidence that water vapour is a major controlling influence on climate. All these calculations support that. And no one, I don't think, would deny it, in fact. I mean, everyone does accept that water is a greenhouse gas. What about CO2? Is there similar direct evidence to support its role in anthropogenic warming? I'm willing to be convinced by such direct evidence, but up till now, I don't see it. I'm not saying that it's definitely wrong, but there's no evidence for it. There's a loose correlation with increasing concentration, we can see that, but everyone is well aware that correlation is not causation. And which causes which when it comes to carbon dioxide? It's very hard, since it's well mixed into the atmosphere, to show any direct effect. Whereas with water you can show direct effect all over the place. Every cyclone is a water effect. And it's caused by heating of the Earth's surface, the ocean surface, so lots of extra water gets into the atmosphere. It's a greenhouse effect. But it's something the Earth has lived with for eons. And it's just part of the way temperature regulation is carried on Earth. So I think the jury is still out regarding the magnitude of the role of increasing carbon dioxide. We rely on this equation. This equation is a laboratory mathematical equation that estimates the forcing effect of increases in carbon dioxide. And this is its theoretical radiative equation that's done line by line for the spectrum that CO2 interacts with, and from that they come up with this number. But it's not a number that's confirmed by nature like the water one is that I told you about earlier, or what I think. It's very poorly correlated with actual temperature changes. You can see that in the way that CO2 is varying. And in fact, the concentration of CO2 in air may follow temperature changes rather than cause them. I mean, this is a point of view that other people have put. And if you look at the Vostok cores, and we'll look at that in a sec, there is... I just wanted to emphasise too the relative amount of atmospheric water. Irrigation is the yellow, the brownish is an El Nino-La Nina cycle difference, and this is the normal amount of water in the atmosphere. So the temperature change that I'm predicting has obviously to be very small. And there's no reason for it to be large, but it is nevertheless of concern. We can measure it. We should be able to measure it. The people working for the IPC have made a lot of this graph. Now what this is this is the normal spectrum, but this one's in the other direction. This is in wave numbers rather than microns. I much prefer this direction, but for some reason they like this. And they reckon here, and this is a comparison between 1970 and 1997. And what they claimed was that there's less brightness from methane between those 2 years. That is, that would suggest there's more methane in the atmosphere. Therefore, it's radiating from a higher, colder temperature. When they looked at ozone, the data are all over the place and they can't say much about that. When they looked at CO2, they managed to get a little area here, which they claimed was a result of the extra CO2 in the atmosphere forcing up the point of emission in the atmosphere. So it would be colder, therefore it would be less bright, the brightness of that radiation from the Earth from CO2. But I was a bit puzzled by the fact that it doesn't actually cover the region of most of the CO2. It's only one side of this dip that you see for CO2 here. Which one is it? It's the one on this side, on that side. What about the middle and what about the other side? Well, you can't look at that because the data's all over the place. It's too erratic. But more recently, in 2007, when people tried to repeat this data, they saw no difference in the CO2 spectrum between those 2 years. It was flatlining. So that makes you wonder. So this is the sort of evidence they're using. And they were gleeful when this was published, because it did seem to be in line with what you might expect from the spectral point of view. But in fact, recent data from the same group of labs is not supportive of these effects, based on the Eyre's Nimbus 4 satellite that was launched in 1970. So we're actually back, I think, even though they're still trying to apologise for this, I think we're back to square one on this approach. And so the question must be asked, well, why isn't it happening if their hypothesis is correct? I'd just like to suggest that perhaps the hypothesis involved, that is that carbon dioxide at the top of the atmosphere has a stronger stranglehold on the amount of heat that can leave the Earth, may not be well founded. I have yet to see evidence that that's well founded. I think that the atmosphere as a whole has got many other corrective functions that are to do with the majority of the gases of the atmosphere, the nitrogen and the oxygen, how far they elevated, how much convection there is, and all these other factors. And that heat can be transferred from one wavelength to another. So it's not as though carbon dioxide has necessarily got a stranglehold. This is a line of approach that I want to pursue with people working in this area as a point of criticism. So I think more data is needed. So far it's not conclusive. So I think we have to, they shouldn't be gleeful about that. It's not working as well when you consider it's now 17 years since they got, 20 years since they first got that confirmation. And things have been becoming less and less certain with time. I think it is important to understand, though, that water absorbs water vapour in all these areas shown here in grey. Carbon dioxide just in this area together with these, but these are not operative. These are the real ones that work in the atmosphere. Methane here, nitrous oxide. So I do think that studying this is important. This is data from Evans from Trent University, and he shows that the water radiative forcing at the tropopause is 90 watts per square metre, where CO2 he claims to be 50, methane 1.7, nitrous oxide 1.3. So you can see the predominance of water, and also the downward flux. So that is, if you take an infrared meter out into the field and measure radiation of certain wavelengths that is coming out of the atmosphere, and there must be, because water is there and it will radiate, it doesn't matter where it is. It's not heating the Earth's surface because the Earth's surface is hotter, but nevertheless you can measure this radiation that's coming down. Presumably the same radiation is going up. The downward flux in winter is 108. CO2 they measure at 32.8. In summer they measured the downward flux for water is 20 times that of carbon dioxide. So this is where a greenhouse effect is actually happening near the surface, and this is what's heating up the surface. Well, this is not really heating it up, but it's maintaining it heated by preventing the escape of heat. If that heat could escape, as in the centre of Australia in winter at night, you find that the downward radiation from water is negligible. And the other gases. So this is, again, just emphasising it's all about water. The weather is about water, not carbon dioxide. Therefore, climate change is also likely to be about something to do with water. Maybe the solar energy is increasing gradually, and that leads to more water in the atmosphere. What the actual causes of the warming is, do we really know? We know that they happen, and that the Earth is never in energy balance. It's always varying. And sometimes there's a trend. And the famous trends that we know about, I was going to talk about clouds, but I think I'll leave that for another issue. On the whole, clouds, low clouds and high clouds seem to balance in their effect. It's very hard to get a clear picture as to whether clouds can be overall warming or cooling, but in any one location you may have one predominating over the other. Obviously, if you stand under a cloud, it's cooler in the daytime, so that's obviously, clouds have an effect. But what is it overall in the net equation? And then if we look at the archaeology or the times and look at the changes in temperature, carbon dioxide concentration and temperature, and the massive increase in carbon dioxide we've got now, as this current interglacial is completed before the next ice age, according to these predictions, that's I would call the Al Gore effect in terms of carbon dioxide. But we now know that water is far less soluble in water when it's warmer. Therefore, when the Earth's surface is warmer, CO2 will leave the water and go into the atmosphere, just as it does in your beer. As it warms up, more and more of the CO2 disappears from the beer. So that's why we love to drink it cold, because it's still got the CO2 in it. Englishmen don't actually agree with that. Yeah, you're an Englishman. And we've got 600 years of temperature and carbon dioxide. A bit hard to see any sort of correlation. And even this rapid increase lately hasn't done much. Not like the change in water in an El Nino, which has done 1 degree. Just draw that to your attention. And in fact, I think it's even more critical than that as far as water is concerned. If you look at the temperature of the atmosphere and the amount of water vapour that it can contain, at minus 10 degrees it's 1.8 grams of water. At 10 degrees it's 7.8. Or at 0 it's 3.8. 10, 7.8. 20, 15. 30, 27.7. 40, 50. So for every 10 degree increase in temperature, the saturation water content of the atmosphere will double. So that's a logarithmic effect in terms of the amount of water that's in the atmosphere. So let's say it's the Milankovitch cycle. Sorry about the difference of sizes there. That ticks it off. A bit of water into the atmosphere warms it up a bit. That tends to draw more water into the system. The more water you get, the warmer it gets. So you really don't need anything much more than the increasing water in the atmosphere, or the absence of it in the atmosphere, to explain the temperature in these ages. And the effect of CO2 is probably secondary. It's not there's no need at all to put in that. That's giving another explanation. It's not needed. The water effect, 10 degrees difference, changes the water content of the atmosphere 50%. So instead, if it dropped now to half as much as it is at the present, the temperature should drop, greenhouse effect, it should drop 10 degrees from 21 to about 11. And you can explain that purely on this linear relationship between the water content of the atmosphere. So, of course, that's not the actual cause of the change. The water is just responding to whatever it is that caused the temperature of the Earth to change. Is it to do with the wobble of the Earth, how much the polar areas are inclined towards the sun, and things to do with the orbit? The Milankovitch cycles are based on a series of about 4 different variables that can mean that the Earth will get more heat from the sun in some ages than it will in others. So that's another. So I'm heading this the relative unimportance of carbon dioxide, just to be a bit aggressive. But the atmosphere must balance the incoming radiation and the outgoing radiation, but never quite does so. It's always overshooting in one direction or the other. And if there's any trend, because there's more heat coming from the sun over longer time periods, well, it will adjust to that. The Earth's very good at this. It's got plenty of experience at adjusting its temperature. The polar ice caps and the glaciers buffer temperature change. I never hear this discussed. But if you've got ice blocks in water, that water will stay at the melting temperature of the ice until all the ice is gone. But if you then add more heat after the ice is gone, the temperature of the water will fall and you'll get more water vapour into the atmosphere. But as long as the ice is there, it prevents that happening. So if we're looking at the North Pole in particular, the South Pole seems quite safe for the time being. Plenty of ice down there, and in fact I think it's increasing. Well, certainly it's increasing in the sea ice anyway. You haven't got that water vapour effect exerted there. In fact, at the South Pole, there's no water at all in the atmosphere. It's an absolute desert. It's so cold. Whereas over the North Pole now, we've got lots of water in the atmosphere. And suddenly the temperature's gone up 10 or 20 degrees over the North Pole. Down in London, the beast from the east sort of balanced that, you know. So if you add up the average, there's probably no change. But that's a water effect. I just can't emphasise it too greatly. If you look at the southern hemisphere, we're in good shape. We're not changing much as far as temperature is concerned compared to the northern hemisphere. So I don't know if they're all going to migrate down here to escape it, but that would be a solution. But if you look at the temperature anomaly, see how the northern area, Siberia, northern Russia, don't think Putin's doing anything there. It's much warmer. This is on a particular day. Oh no, a month. February 2018 compared to the average of 1981. So it's, you know, something's happening. And it's not caused by carbon dioxide, because carbon dioxide is pretty much the same everywhere on the Earth. Bit more in the northern atmosphere, but that's only because they're making more of it up there. And if you look at the temperature anomaly for the southern hemisphere, that's global. This is since 1980. Of course, this is an exaggerated scale, but it does let you see. So this is the warming period since 1980. Northern hemisphere is much greater than the southern hemisphere, according to this data set from the university, from Norwich in England. So to sum up, there is a greenhouse effect warming the Earth, but direct evidence shows it's controlled mainly by highly variable water. Now, given we go, and so I make my point about carbon credits and greenhouse credits. If we're worried about carbon, we should be at least not worried because it's going to affect us directly by managing water and how much water is in the atmosphere. And if we're worried about cyclones, it's going to be something to do with the extra water in the atmosphere and how can we manage that. So I reckon giving greenhouse credits would be a win-win situation, safeguarding our water resources for food production as the world population continues to grow. And I think they've omitted something important. In the talk I gave last year, I talked about the thermodynamics of the atmosphere. And I talked about virial action, the virial theorem, and its effect on the temperature gradient. And I intend to get back onto that, but I felt that was a bit too esoteric to be talking about it at a conference. It's something that should really be done in a workshop. But if you put more water vapour in the atmosphere, it will change the temperature gradient because and it will reduce the density near the surface. because water is lighter. But pressure is decided by the numbers of molecules, the number density, not the mass of the molecule. The pressure at the surface is a result of the weight of the whole atmosphere, weighing down, but there's also a thermodynamic pressure, according to the ideal gas law. And the atmosphere will try to adjust itself so those two equal one another. So if you have a hot spot, you'll get a thermodynamic high pressure. Or if for some reason we dump a whole lot of extra water in the atmosphere, you'll get a pressure weight effect. So the pressure should go up slightly during an El Nino, and you could calculate what that should be from the weight of the... It should go up by 4% globally, because it's just the extra water. So if CO2 is added to the atmosphere, it also is said to increase the resistance to heat flow. It traps a bit of heat, but negligible amount near the surface. Even the ICP scientists don't think it's important near the surface. They only think it's important at the top of the atmosphere. And that's because the extra CO2 means the concentration falls off less rapidly with height. So you only get to the point where its radiation can go to space higher and colder. That's the basis of their greenhouse theory. It's not about heat reflected back to the Earth's surface. It's about carbon dioxide being able to prevent the extra heat leaving the Earth. So that dip in the centre of its spectrum will fall, particularly on the edges, according to their theory. I'm doubtful about this. I think the atmosphere has got other ways to adjust to get rid of energy. I think it's got other ways of adjusting. It can't adjust the... well, it can adjust the absorbed... that should be ASR, shortwave radiation. That's to do with the albedo. So if we paint all the houses of Sydney white, we'll reflect a lot more heat. It'll be like Jerusalem, which have got all its houses painted white. And they do that to keep the place cooler. And they know through experience that works. Carbon dioxide then, I think, should actually depress the atmosphere a bit because it's heavier than air. And whether that's a significant effect or not, I've still got to work out. I haven't spent enough time doing calculations. But if it depresses the atmosphere, that would mean it could release more heat. So it could be that carbon dioxide, when it gets to a certain level, you might say this is speculative, but it certainly is, but it could mean that CO2 eventually cools the Earth. But I don't think by a great deal. I really do think we have to look at water in its various forms and places, particularly on land versus the sea. I think two effects with CO2, one warming and one cooling. Which one wins, I'm not sure. I have to do calculations and try to do experiments. So the atmosphere has got all these different ways of adjusting. And I don't think that CO2 has got a stranglehold on the atmosphere and it says this is how much heat can leave the Earth and no more. I don't think it can be that precise. It's just to finish up, you might remember my model. I'm not going to talk about it here, but this is the one today. But this is the one that I'm working on, and it has different ways of calculating the virial temperature gradient, the important equalisation of pressure between gravity. I'm a little bit doubtful about one of the central planks. That's the hydrostatic equation. I'm a bit doubtful about that because the density depends on the temperature at the surface. So the density profile varies. The virial theorem itself enables me to calculate. I'd see that water is a fairly small proportion of the total gases of the atmosphere, but it's dynamic. It has a huge amount of energy that it releases. And every thunderstorm, which are multiplied by thousands, Now you can see these things on the television showing all the lightning strikes all over the place. It just gives you some idea of the amount of energy that water is able to release from the latent heat of evaporation. We did discuss about evaporation cooling the surface, and that's true with irrigation, but it doesn't get rid of the heat. The heat's just gone up into the atmosphere. So thanks very much. I think I'll conclude at that point.
Thanks very much, Ivan, and please stand by. For those that might like to raise a question, I'd like to pass the microphone to you so we can pick the question up rather than ask it from the floor and not have the audio captured on the video. If I could ask maybe the first question anyway. You mentioned that Andy Pittman saw your presentation recently, Ivan. That's good, and that he claimed at least one of the GCM's global circulation models captures the effects that you're talking about here. Did he give you an indication as to when that was included in the GCMs, and was it as comprehensive as a detail as you've presented this evening?
Well, what he said was that my claim, that it hadn't been included in the GCMs was incorrect. He said it would have been correct a couple of years ago. And I'm intending to write to him after this presentation to ask him if he's got any more publications. I did find the one that I think he's talking about, and that was published by the Goddard Centre. But there had been an earlier paper that really had the same theory as I did. And they did get an effect, but not as great as what I predicted. Modelling, using a model, not my measurements. Now, the Goddard Space Centre, and that Andy Pittman was obviously referring to, must have got bothered by that publication. So they did their own study. But the problem with the study is that they've done it as global averages. So I think the model has totally lost sensitivity for seeing this effect from the water for irrigation, which goes on in particular environments, dry environments. They even included the ocean and the effects of irrigation on the ocean. Well, I can remember Tarly talking about irrigating. Where's he? He's still here, isn't he? Oh, there we are, yeah. Irrigating last time, but I think the ocean is irrelevant to what I'm talking about. I mean, it's part of the whole system, obviously. So where do I stand with Andy Pittman? I'm going to write to him. I'm going to ask him for more detail. I'm going to criticise the paper that I've got because I think it's flawed. And I may tell him something about what I've been doing with Lake Eyre, because their modelling would not predict what I've actually seen and observed from that data from Lake Eyre. So as far as I'm concerned, that's the sort of scientific evidence that I'm seeking to make decisions about these effects on climate. Yeah.
Yeah,